Okay, we're on. Good. So, okay, so we've already done the compressed matrix multiplication. We've covered all of that. We've done a fair amount of the random function classes. So we had the empirical kernel map. We've looked at the basic expansion for fast food. And so what we're going to do today is a couple of things where we look into the detail for, how to go from random kitchen sinks to fast food and do various things efficiently. And then in the end, if there's still time permitting, I'll briefly cover reservoir sampling and a very nice recent application of that. Okay. If there are any questions so far, let me know. Are there any questions from Monday? Anything that was not clear on Monday? Wow. This looks like Ina did an absolutely terrific job because nobody has any questions. Okay. Who recalls one of the things that she did? Can you tell me one of the things that Ina did? Come on, if there are no questions, you must all remember something. So, guys, come on, give me a hand. Okay, so we did this. Okay, good. Yeah. What else? Mm-hmm. Okay. Nice. Anything else that you guys recall from last? Fun? Heavy hitters? Yes. Yep. Awesome. Yeah. So actually, TAs don't count here. That's unfair. I mean, you're supposed to know all of this, but everybody else who didn't know the stuff beforehand. Who else recalls something? Awesome. Thanks. Okay. Any questions about this? Everything clear? Everything totally clear? Awesome. Good. So my guess is, yeah? Don't worry, we will pick them up again anyway. So yes, no, but ask. Go ahead. No, I mean, because otherwise, giving the background itself will take some time. No, but I mean, if you tell me now what the question is, I can add it better in. So would you please kindly tell me your question? Yes. Okay. Great question, and your question shall be answered in the form of group theory. So a lot of the choices of why we use, for instance, the Fourier basis has to do with group theory. And we'll go into details of that as we go along. Okay, that's good. So the first useful thing that did Ina cover matrix Höfting? Matrix Chernoff bound. Did she cover? Okay. Okay. Good. So, so here's this is one of those big innovations that happened over the past 5-6 years. Is that people have managed to actually get concentration of measure inequalities, not just for individual entries of matrices, but for entire matrices. We're going to devote a special lecture just on concentration of measure for matrices. This is probably what I'll be doing after Subrit is done with some more of the optimization parts. So I'll be covering a fair amount of concentration of measure for matrices because it's fairly new and would not be taught otherwise in randomized algorithms class. But let me just give you a brief advanced preview. And so here's the thing. So standard chain of bound basically goes as follows. Suppose I have some random variables. So suppose I have some random variables xi which are drawn from their own distribution pi. Okay. And I know that the xi's are in some range between ai and bi. Let's see whether there are any pins that are made less for blind people, because these crayons are, I mean, 1 inch thick. Oh, let's see.
Do you guys have any ideas where some more crayons might be hiding? There are parts of chairs and playing cards and other things, but even sugar? It's just junk.
Okay, let me try that. Yes, thanks. This looks equally bad. Okay, no. Okay, let me see. There are about 10 pieces that might make up 1.5 crayons altogether. Okay, thank you. Yeah. Sorry, otherwise the font size is just too gigantic. So suppose I have some random variables xi ranging from ai to bi. So this should not be any surprise because we've already done this before, right? Then I can define c squared to be the sum over I bi minus ai squared. And in this case, I have the theorem that the probability that sum over I xi deviates from the sum over I expectations of xi by more than epsilon is bounded by 2e to the minus 2 epsilon squared over c squared. Now what happens here is that this quantity here is basically, it behaves like a variance, right? So quite obviously this is an upper bound on the variance of random variables. The variance could be a lot smaller. So if I had a random variable whose density looks like so, right, and here's ai and here's bi, then this bound here will be lousy. But if not, this is actually a pretty good proxy. So now if I have a matrix, okay, and let's say I have some matrix M, and it's given by, okay, let me just make sure I get this exactly correct, and it's given by a sum over I mi. And each of those mi's are drawn from some random distribution pi of mi, right? Then I might want to ask something like, well, how rapidly does the sum of matrices converge to the total matrix? And what happens now is quite obviously those terms may actually be correlated with each other, right? So a simple example is where these matrices, where we're talking about covariance matrices, or matrices of second, third order moments or something of that form. So we all know that, for instance, the expectation of x transposed, which is useful for a covariance, right, can be written as 1 over n sum over I equals 1 to n xi transposed, right? So here we can define those guys here to be individual matrices mi. We know, let's just call this thing here C. Now I know that the expected value of each of those MIs is C. They're all drawn independently from the same distribution. You have this averaging term here. So now the interesting question would be, will I be able to get better bounds on conversions for the entire matrix than I would be able to get otherwise pointwise? Because what you can clearly see is, if I wanted to get a guarantee here using this for the entire matrix, sure, I can treat each of the entries as a random variable and then get pointwise guarantees and then apply the union bound. But if this is now an if this is a d by d matrix, I will have to invoke d times d plus 1 over too many of those instantiations to get anything useful, right? And this, of course, is bad because it will cost me 2 log d extra confidence, which is a problem. And so the guy who's been really instrumental in getting guarantees of this form is Trop. Joel Trop. And probably one of the more useful papers, as in easier to read papers, would be the one by Trop, Mackey, Jordan, and then there's a fourth author whose name I forget. And this would have come out around 2013 or so. And we'll actually go through this paper in a fair amount more detail in another later lecture. But this is just as an advanced preview of what you can get. So the theorem that you get from them reads as follows. Given some matrices, without making too much of a mess. Wow. Oh, they're the thick ones. No, I wanted to have the thin ones. Hey, don't worry. Don't worry. Don't worry. I'm sorry. Makes it worse. Hey. Yeah. So basically what I'd be interested in this case up here, is to look at the difference between sum over I mi minus their expectations. And for instance, you might ask something like, does the norm of those matrices do something terribly useful? So basically, I might ask something like this. How large is this? So I'm going to denote these matrices here by yi. And they have the very nice property that their expected value is 0. So now here's the matrix Chernoff. Given yi, drawn sum from pi of yi, with the property that the expected value of yi equals 0. So that's exactly what we have up here. And furthermore, that the yi squared matrices are less equal than some ak squared. So this is basically the equivalent of this box constraint. So we basically need to make sure that in their norm, those matrices here are bounded. Then the probability that lambda max of sum over I yi. In other words, this is the norm here. So in control theory, this would be the infinity norm because it's the largest eigenvalue. Right? So if you've ever done control theory, there's H infinity, H2, and H1, and so on theory, and that's basically what you do with the norms. And basically, H infinity would be the largest eigenvalue, H2 would be the Frobenius norm of the residuals, and H1 would be just the sum of the singular values, so eigenvalues, depending on whether they're positive semi-definite. So, but basically, the probability that this is greater than epsilon, so that's the equivalent of, this deviation term here, is less equal than d e to the minus epsilon squared over 2 sigma squared. So we still pay a dimensionality dependence here, but it's not too bad. And now this quantity sigma squared is 1/2. Oh, awesome. Thanks. That's great. Thanks. You're fabulous. Let's get rid of this crap. Oh, even different font colors. Okay. So this is nothing else than the sum over AK squared plus the expected value of those YK squared. Okay, so in other words, I now have something, and I have of course sum over K. So you can clearly see if they're all drawn from the same distribution, this will go like, square root K. Sorry, this will go like K. But since I'm normalizing by 1 over n, this will go like square root n, will go like 1 over squared n, so the variance will actually decrease, so this is a good thing. Sorry, this will go like 1 over n, so the variance will be fine. So we'll basically have an independence up here, which gives us the usual rates that we get from standard Chernoff. And sure, we still have a log dimensionality dependence, but this is now much better than first getting a pointwise guarantee on all the entries of a matrix, and then trying to use that to get a full guarantee for the full matrix. Just to make that point, if I have some matrix M, and this matrix M has basically a pointwise guarantee whereby Mij is less equal than epsilon, right? Then from that it follows that the largest eigenvalue of M, of course, can be as large as d times epsilon. There's a very easy way how you can construct this. You basically make all the entries of this matrix epsilon. So if I multiply with the vector for ones, which is the eigenvalue, and this is the only it's the eigenvector, which is the only eigenvector of that matrix, it's going to be d times epsilon that gets out of it. So you can clearly see that if I just first apply something pointwise and then want to get a guarantee on the matrix, you get a fairly lousy result. Whereas all those matrix Chernoff results do not suffer from that problem, right? So this is bounding the quantity we're interested in directly as opposed to in a very roundabout way. And this, of course, is quite useful. So that's as much as I wanted to say about matrix Chernoff. The reason why we actually looked at that is because when we do random kitchen sinks, we effectively end up dealing with such quantities and also other random function classes. Because if you think about it, all those random function classes, cool, addition theorem for cosine and sine, are of the form I'm mapping x into 1 over n f1 of x or phi 1 of x up to phi n of x. We might actually need this later, so this is useful. That's connected there. So, so these are now some random basis functions drawn from some pool. In the case of the empirical kernel map, these functions were actually some function kappa of x and x prime, right? So for empirical kernel map, these were phi I of x were functions kappa of xi and x, where the xi's are drawn from the distribution where the data came from. Okay, so this is Shulkov, Tsuda, and others about a decade ago. So about 2 decades ago was the very infamous NIPS reject by Bradford Neal. Around 94, in which he proved that that neural networks with random basis, random hidden units, and the number of basis functions going to infinity would give us a Gaussian process. Did Ina go through the proof of that? Okay. You did? Okay, good. So, yeah. So basically, there we had that, those phi i's of x were just, some nonlinearity gamma of, let's say, w I dot x, where w is drawn from some distribution p of w, and you would have then Gaussian weights with those. So this is basically what for about a decade or so killed neural networks, and then they came back with a vengeance, right? So basically, if I have random basis functions, I have a bit of input, then you can effectively, from those hidden units with linear combinations, then model a lot of things, and on top of that, the proof was basically that this is still well behaved. Okay. So recent reinvention of this concept is in this paper, the random forest kernel, in creating other kernels for big data from random partitions. So this is Davies and Garamani. This is from 2014. I think they submitted it to ICML. I don't know whether it went through. Surprisingly, they do not actually mention any of this. Okay. And here's essentially their argument. So they say, well, if I want to ascertain the similarity between two objects, what I could do is I could, for instance, have a distribution over sets. So I have some distribution over sets. S are drawn from some P of S. And I can define as a kernel K of x and x prime to be the empirical estimate of the probability that x and x prime are both in the same set. In other words, I have x in Si, x prime in Si. And then the argument is that, yes, you can actually store this very efficiently for large amounts of data, because basically now what you're doing is for each x, you're going to compute the set assignments for each of those observations. This isn't exactly very large scalability if you think about it. The reason for that being that, well, each of those set memberships well, I will still need to, you know, store at least one bit of information. And so if I have a lot of data and a lot of sets, I will still need to store order m times n storage. Right. The similarity, however, is actually reasonably cheap, because what I can do then is I just do bit comparisons. They actually do something slightly more intelligent than this. So what they do is they basically say, well, actually, I'm not going to partition only into random subsets, but I'm basically going to partition my space into, you know, just random set partitions. So we basically have Sij, right? Sij prime, and so on. And then the argument, the question again is, well, do 2 points belong to the same set? Now you can easily see that this is equivalent to this up to scaling factor. Because I can simply, you know, use this double integral of, well, let's integrate over all those sets, and for all sets but one, this will vanish. So I just need to look at what's the probability that 2 points at all will lie within the set, and then I go through it. So that's why it's actually, yeah, those two are equivalent. If you were to store things directly in this way, you would need to store the set indicator here rather than just one bit. So this is possibly actually computationally a little bit more expensive, depending on how you store things. Any questions about that so far? Yep. Yeah. So the premise in the Neal paper. Okay, so the Neal paper, and this is essentially what started Gaussian processes in machine learning, was the fact that at around that time, people were building bigger and bigger neural networks. And so he asked the logical question, well, what if you built a neural network with an infinite number of hidden units? And the question then is, you know, what kind of function classes can you get if you do this? And the assumption was that you would have Gaussian weights for each of those basis functions. And then he took the limit to infinity of that. So of course, each of the weights would, you know, go to 0, but would go to 0 more slowly. And in this case, you then can show that you get a Gaussian process with well-defined covariance function. They are random. And so the proof was that basically as long as I have Gaussian independent weights for each of the coefficients, for regardless whichever basis functions you would pick, you would get, you know, a kernel. And the kernel is actually easy to work out from that. It's basically just, you know, the expected value of, you know, this function gamma of, you know, let's say parameter wi w dot x gamma of w dot x prime. So this would be the kernel k of x and x prime. This of course gives you a gigantic freedom in terms of which kernels you pick, and if you don't like this particular gamma function, you could pick another parameterization. It would go through in the same way. Quite amusingly, it then took, yeah, another 6 or 7 years until people made the reverse argument. So this is a paper by Chris Williams from '98. Williams, and he basically showed the equivalence between just general Gaussian linear models and Gaussian processes. Does everybody know that connection? Okay. If not, let me quickly go through it because it's a rather useful result. Yeah. Yeah, unfortunately the sines and cosines have to die. Here's the idea. Suppose I have some function f of x, which is given by the inner product between phi of x and w. Right? Standard linear function. And I know that w is drawn from a normal distribution with, let's say, zero mean and unit variance. Right? So, I can solve my estimation problem this way. So, for instance, if we just build a nice linear classifier, this might not be a terribly bad assumption. For instance, a maximum posteriori estimate would then be something like I minimize over w, some minus log p of all the data given x and w, and then I add to that plus 1/2 norm of w squared. So I could do this. And this is like a, very standard model. Now, in Gaussian process land, you make a very different assumption. You make the assumption that f is drawn from a Gaussian process that's indexed by a mean function mu and a covariance function k. What this means in practice is that the point evaluation, so f of x1 up to f of xn, is drawn from a Gaussian with mean mu of x1 through mu of xn, and a covariance matrix k, where this is now given by basically where kij is just k of xi and xj. That's how you define a Gaussian process. So what this paper showed is that those two things are equivalent. And here's how it goes. So first of all, to note, well, if this is my assumption, then f of x1 through f of xn are clearly going to be Gaussian, right? Just because I'm linearly transforming a Gaussian, and this will hold for any index set. We know that for a Gaussian process, this is the only thing that I really care about. So the only thing that I need to do now is, well, let's actually give it some mean mu bar. Otherwise, it gets a little bit boring. Okay. So now all I have to do is just identify the mean and covariance function. So for the mean, well, all I have to do is just compute the inner product, the expected value of f of x, which is now nothing else but phi of x dot mu bar. So this is now my function mu of x. Now, the second thing that I need to do is I need to look at the covariance function. And so I need to look at the covariance between f of x and f of x prime. And you can immediately see that this is now, since we can take the expectation of a w here, it's going to be nothing else but phi of x dot phi of x prime. And that's the paper. That's the entire idea of it. So it's, in hindsight, such an obvious thing, right, to see. However, nobody saw it until before Chris Williams saw it. It's kind of embarrassing in a way. But yeah, it's quite cool. Yes? That's a very good question, actually. Can I always find that? Well, I could cheat. So cheating would be that I simply define, okay, so let me show you how I can cheat. I can cheat by saying phi of x is just delta x, problem solved. But that's probably not what you wanted to hear. So you could ask something like, you know, what is the dimensionality of the data? Basically, you just look at, you know, the subspace that spans all the mu of x's, right? And this will then give you a more reasonable representation of this mu. Based on that, you can then try up to rotations and so on to identify how you can write, you know, this as, so you basically, it's a dictionary learning problem, so you have a lot of, you know, ambiguity here, right? Because what you're basically asking is, you know, if I have some vector mu, can I write this as some design matrix x times some other vector alpha, right? Yeah. So, no, but I mean, this is basically, you know, these are your features, right? So, obviously, this is heavily underdetermined, this problem. So, what you need in order to make this work, and it's perfectly reasonable question, is you'd have to make some assumptions on the x's and on the alphas. So basically what I wrote here is basically I said, well, you know, let's just make x diagonal and then alpha equals mu and everything's fine, but that's cheating. I don't learn anything. If I have a very specific assumption on x on my design matrix, then I can quite possibly solve this for alpha. So if I have a set of basis functions, then the problem becomes fully determined. It can actually become overdetermined, and I just then minimize the least squares problem. This is called regression, right? So depending on what additional constraints you impose, this can be a complete crapshoot, or it can be very easy to solve. That's a very nice question. So in some cases, for instance, when you do multitask learning, you know that your covariance function, for instance, has a very specific structure. So for instance, in the context of computational advertising, you have two sets of indices. You have one set of indices being the advertisers, so basically, you know, Coca-Cola, General Motors, Toyota, or whoever, or Amazon, whoever want to sell you some ads. And you also have the attributes. And so now you have a covariance function over both things, because maybe, you know, for Coca-Cola, people care about the, well, it's the age that's relevant, and maybe for General Motors, it's basically, you know, whether you know, live in a place where people buy trucks or not, and, you know, stuff like that. So you can actually write this out as a joint, as the tensor product between two covariance functions, and you can then do inference in this. So there's a paper that we had at Wisdom this year that goes into a fair amount of detail on how to do it, and so this paper is by Ahmed. Das and smaller, and it's WSD M 2014. Yeah, that's the one here. Sorry, I didn't want to say that, but yeah. So this has a fair amount of detail in it. There's actually a couple of follow-ups that you should be doing based on that. Basically, we didn't really do the full joint covariance matrix inference. So this would be actually a very neat, albeit maybe not terribly deep follow-up based on what we have there. Imposing then further hierarchy and structure on that would get you further. Okay. So now we've digressed a substantial amount from the random basis functions, but I hope it helps you put things between basis functions and kernels a little bit more into context. Any more questions about that directly? So this is the random forest kernel. I'll just pass it through. It probably is not as big data compatible as the headline is, but I am sure this helps for getting a paper published. Okay, good. Now on to fast food, and you know, where do all those function classes come from, and you know, how does this all relate? Good. So, how many of you in the room know group theory? Okay. Who recalls representation theory? Not many hands go up. Okay, so not many happy smiling faces. This is effectively something that we'll sort of kind of at least vaguely need to touch upon when we look at where do those basis functions come from and why can I actually do certain of those operations. Who's ever heard of spherical harmonics? Okay. In more than 3 dimensions? Essentially nobody. Okay. So this used to be a hot topic about 100 years ago. Yeah, so this was beaten to death by lots of French and German mathematicians, which is why a lot of those things have theorems and formulas and names with German or French names. So for instance, Legendre polynomials, right? Or then there's a book by Magnus over Hettinger and Sony, Germans, yeah. Or yeah, there's basically a lot of that kind of stuff that was done. So here's basically what's going on. So when we have a kernel, let me start with a very simple case, namely the translation group. So the translation group is something very simple. Tx, okay, so group is basically, you know, a set of elements that you can concatenate, and the concatenation is back in the group, right? That's essentially what it is. There are some very special groups that are called Lie groups, and their property is that if you look at those groups near the origin, which is basically the identity element, then the geometric structure around the origin tells you everything you need to know about the group. In the translation case, that's a very straightforward thing, because it basically means if I tell you how shifting things around works over here, you know how shifting things works over there. You just need to know how to get from here to there. Then you can apply the same operations that I showed you here over there. Same thing applies for the rotation group. Now in the rotation group, if I tell, and obviously you can define rotations in more than 3 dimensions, if I tell you how to rotate things around the identity, you can rotate things further around anywhere. There's one important difference between the translation group and the rotation group. Does somebody know what the key difference is? Take the box. What? The order matters. Exactly. So in other